Alright, welcome back. In this video, we're going to talk about two-dimensional motion. And first, we're going to recap what we talked about in the first semester about motion just in general. So we talked about a lot of situations where an object was moving back and forth on a straight line, and we frequently thought of that line as the x-axis, so we said that the position was like x of t. And the velocity of that object was the rate of change of its position, so we call that v of t, and that was the first derivative of position. And then we also talked about acceleration, which was really the rate of change of velocity, and we called that a of t, and we computed that using the second derivative of position. And then there was this speed thing, and speed was a lot like velocity, but we took the absolute value of it, okay? And then we found total distance traveled by an object, just like total distance without regard to, forward, backwards, and change in position. We call that displacement. That was something different. We found total distance by taking the integral of speed with respect to time between two time values that they gave us. And now for two dimensions, we're going to see that the approach is exactly the same. Position, we're still going to have an x of t, but there's also going to be a y of t because there's two dimensions, so it's just like a coordinate pair. The velocity is going to be still the derivative of x, but also the derivative of y, because if the position is a vector, then the velocity will also be a vector. Okay, and then the acceleration is itself also a vector because it's going to be the second derivative of position. And so it'll be x double prime of t and y double prime of t. And for us, for two-dimensional motion, speed is still going to be the absolute value of velocity. And total distance, we're going to calculate this the exact same way using the integral of speed. But the question there would be like, well, what do you mean by the absolute value of v if v is a vector? And that's something we have not talked about in this class. It's like the length of a vector. So if speed is the absolute value of velocity, like it says, and velocity is a real number, computing speed is easy enough. We know how to take an absolute value. But you may not know how to take the absolute value of velocity if it has two components. So we're going to sketch w in the xy plane 3 and 4. Okay, so it starts from the origin and goes to the point 3 and 4. Okay, and if we want to find the length of w, really the absolute value, or the length of w, is going to be the distance from the origin, just like absolute value was the distance from 0 on the number line. Okay, so if we kind of break out this diagram and turn it into a right triangle, we might see that the horizontal leg has length 3, and the vertical leg has length 4. And if okay, 3, 4, 5 triangle, that's going to be a 5. But really what's going on here is we're doing the Pythagorean theorem. We're saying the length of w is the square root of 3 squared plus 4 squared, which is going to be the square root of 25, and that's 5. So we could say that if we have just some vector in general, a and b, and that arrow over the x, that's something you would see in other math courses, but not in AP Calculus. They don't use that decoration for a vector. So you might see it here a little bit if you take my multivariable calculus class next year. You'll see that all the time, all over the place. But not really beyond this page in AP Calculus. Okay, but we would find the length of x by doing the Pythagorean theorem on its components. So that's, that's just going to be the square root of a squared plus b squared. It's probably gone. The key word there was the length. Yeah. And what we're really going to need to take the length of in this class is velocity vector. And it's almost the only thing we would need to take the square root of the sum of the components squared. Not the only thing, but almost the only thing. So if we have vx and vy, which is probably what you would see in a physics class, I'm going to call this x prime of t and y prime of t because that's going to be a really important connection for you to make. It's going to be the square root of, vx squared or x prime of t squared plus y prime of t squared. And if we want to find the total distance traveled for an object moving with that velocity vector x prime of t and y prime of t, I think I actually meant to change the vx and vy to x prime and y prime, just forgot to do the other one. The total distance traveled, we're still going to integrate the speed. Okay, so we've got that, and then we're going to incorporate that square root in there that we know is the speed. Okay, and if that integral looks familiar, it's like, yeah, we dealt with that one last time. That was the arc length integral. And if you think about it, if the arc, the actual curve, the two-dimensional curve, is the path of the object, it would make sense that the length of the arc is the total distance traveled. Now, equipped with those formulas, we're ready to look at some free response questions. And parametric equations or 2D motion, a very common situation in AP Calculus free response, at least for the BC exam. So for time t greater than or equal to 0, a particle moves in the xy plane having position x of t, y of t, and velocity vector given by cosine of t squared and e to the 0.5t. Okay, now the first thing I really want to point out is that those are x prime and y prime. Okay, that's a really important connection to make. I already mentioned that once. But that we need to know that x prime of t is cosine of t squared and y prime of t is e to the 0.5t. We're also going to need to, if we're allowed a calculator, which we definitely are going to be on the second question of free response, we're going to need to load those into the calculator immediately because we're going to definitely want to work with them. And I'm going to recommend that you type these in as f of x and g of x, just because x of t we have seen is I don't totally understand why it's troublesome on Desmos, so I just totally avoid it and call it f of x. If you need, you could add in a note, like to yourself saying, okay, x prime equals f and y prime equals g. Okay, that might be helpful. Okay, you could leave that there for yourself. Okay, but if we want to find the x-coordinate of the position at time t equals 2, we're just going to start with the x-coordinate that we know, x of 1, and we're going to use an integral on the x-coordinate of velocity. Okay, so x of 2 is going to equal x of 1 plus the integral from 1 to 2 of x prime of t dt. And we know that x of 1 is 3. And we know that x prime is cosine of t squared. So we're going to add that in, and then we're going to go to the calculator and say 3 plus the integral from 1 up to 2. Now, x prime is f. We can even call it f of t dt, because that's just the variable of integration. And that's going to give us 2.557. And that's the x-coordinate of the position. Okay, so we're good there. And then we're going to move on, and we're going to say, okay, for t between 0 and 1, there is a point on the curve at which the line tangent to the curve has a slope, that's dy dx, of 2. So dy dx equals 2. We know that dy dx is y prime over x prime, and we have formulas for those. And I think that equation would be enough, for justifying our answer. But just to be clear about what's going on here, I need to take that e to the 0.5t and divide by cosine of t squared and have that equal 2. So that's what I'm going to use the calculator for. I'm going to clear this out because I'm done with that. I'm going to say let h of x equal g of x divided by f of x. Okay, now that's kind of a lot to look at, especially if I zoom out. So I'm going to actually give it the interval they told me, 0 less than x less than 1. Okay, and then I'm interested in where that equals 2, so I'm going to graph 2 also and, call for the intersection. That'd be 0.840. So over here, that's t equals 0.840. Yeah, there it's a point. Okay, so that's the only place, and that's it for that one. Okay, now we want to find when is the speed equal to 3. Okay, so the speed is the square root of x prime of t squared plus y prime of t squared. If that is 3, we're going to set that equal to 3 and solve that equation. Okay, so I'm going to get rid of these. Okay, h, that was the slope of the tangent line. Now we might take a look down at the rest of the problem. Yeah, okay, there's not going to ask me anything else about slope, so I can get rid of that and say, okay, speed is the square root of f of x squared plus g of x squared. All right, that's going to be my speed function. I want to know when it is equal to 3. So I'm going to graph y equals 3 and say 2.196. And so, okay, I've got that there. That was the only time that happened. Ready to move. And then the total distance traveled, okay, we integrate the speed, and I've already got the speed loaded in here as h of x, so what I should do is integrate from 0 to 1 on the speed, okay, but over here, I'm going to just call that h of x dx or h of t dt, right, and we're doing the same thing. Let me actually show you that. There you go. 1.595. Wait, whoa. Yeah, I'm not totally sure how I got that the last time I worked this problem, but okay, I kind of remember that was the number I got in class, so I'm satisfied with that, and I'm going to move on. Now, The next one I've got is, pretty typical, pretty standard one. But I did add a little bit of intrigue at the end. This one's from 2006 Form B. We're going to start by writing an equation for the line tangent to the curve at the point 2 and -3. So we've got our point already. They just told it to us. That's times t equals 1. For the slope, I'm going to need y prime of 1 divided by x prime of 1, because that's the time when that's happening. Definitely going to use the calculator for that. So I'm going to go here. Okay, y prime of 1 would be g of 1 divided by x prime of 1 is f of 1. I get 2.781. I report that, and then my equation will be y minus -3 equals 2.781 times x minus 1. Right. Part B, we're asked for both the acceleration and the speed of the object at time t equals 1. So we're going to set up for the acceleration and for the speed and make sure we're declaring two different answers. And now the acceleration is going to be a vector. We talked about that earlier. It's going to be x double prime of 1 and y double prime of 1. So that's going to set up to be my values there. What I'm going to need is, okay, x double prime is going to be f prime of 1, okay, I get -0.423, and then I'm going to just go over here and change that to a g and get -0.152. And then for my speed, I'm going to need to consider the square root of x prime of 1 squared plus y prime of 1 squared. So I'm going to go over to the calculator and say, okay, square root of x prime of 1 is f of 1 squared plus y prime of 1 would be g of 1 squared. I get 1.139. And there we go. Then if I want to find the total distance traveled by the object over the time interval 1 to 2, I'm going to be integrating that speed. So I should be able to, kind of like adjust this entry here and throw an integral around it, or at least like cut and paste it in, change the 1's to t's, and, I think that should work. Right, because the integral we want is this integral from 1 to 2 of x prime of t f of t squared plus y prime of t g of t squared. Okay, so we are going to throw an integral around that, the integral from 1 to 2. Does it think that's in the integrand? I don't even know. I think it's working. Yeah, 1.059. This is great. Okay, so there we go. Computed the total distance. Part D is a little more interesting. Is there a time t greater than or equal to 0 at which the object is on the y-axis? Explain why or why not. Okay, I'm going to draw a picture of what I know for sure right now. And that's that at t equals 1, the object is at the point 2 and -3. And I think that might help me a little bit think about what would need to happen if the object was on the y-axis, right? If the path went through here somehow and touched the y-axis, I don't know, before or after t equals 1, we'd be seeing a place right here where x was equal to 0. Okay, so what we really need to be thinking about is like x and its rate of change. So I think what I'm going to do is turn on the graph of x prime of t. That would be f of x. But it said t greater than or equal to 0, so I am going to make that restriction, x greater than or equal to 0. And then we're going to graph that, and I'm seeing, okay, this is always positive and rapidly approaching 0. Okay, so dx dt is always positive. So that means after t equals 1, the object is only moving to the right. Okay, so it's not going to be hitting the y-axis at any time after 1. So I think what we need to consider is what is the x-coordinate at time t equals 0? Because if the x-coordinate at time t equals 0 was, say, negative, we could use the intermediate value theorem on x of t, right? We've got a derivative, we know it's continuous, we can do that. So what I really need to know is what is the value of x of 0? X of 0 would equal x of 1 plus the integral from 1 back to 0 of the derivative of x. Okay, we'll definitely be able to use the calculator for that. So I'm going to say x of 1 was equal to 2 plus the integral from 1 to 0 of, not x, that was f of t dt. Get 1.224, yeah, okay, 1.224, I wonder if that was going to happen. This is greater than 0. I actually hadn't worked this one, I just knew that I was going to have to analyze dx dt. All right, so this is greater than 0. And since, yeah, dx dt did not have any sign changes, I know that I only, so draw t equals 0. X was 1.224. So it was, I don't know, maybe somewhere over here. Y was probably very different, but t equals 0. Between t equals 0 and t equals 1, x only increased, so I know there was no time. Okay, so I'm going to say no, specifically to answer their question. X of 0 is greater than 0, and x increases for t greater than or equal to 0. So x does not equal 0 for t greater than or equal to 0. Okay, so now for the last part, and this may exceed the scope of AP Calculus, actually finding the equation of the line, the slope of the line as t approaches infinity. I've seen that one before, but the equation, this one is doable, and I found it interesting, so we can do it. What we're going to need to do is start with the slope. So dy dx is y prime of t over x prime of t, and we've got an equation for that. That's secant of e to the negative t divided by tangent of e to the negative t. And then we're going to need to consider the limit of this slope as t approaches infinity. And what I would point out about this is as t approaches infinity, e to the negative t goes to 0. So we're going towards secant of 0 divided by tangent of 0. But tangent of 0 is 0. So we've got slope going towards division by 0. And so either we're going towards 0 over 0, which that would be weird. We'd have to do like L'Hopital's rule or something. Or something else. But if you think about secant of 0, that's 1 over cosine of 0, and that's going to be 1. So if the numerator is going towards 1 and the denominator is going towards 0, that limit just doesn't exist. And if that limit doesn't exist, that means we're approaching a vertical line. Okay, so I've got a vertical slope. Now, to find the actual, location of that vertical slope, I'm going to need to figure out, well, what's kind of the limit of x as t approaches infinity. So I'm going to think about that. So the limit of x of t as t approaches infinity. Well, I'd probably do the same thing I did up above, right? I started at t equals 1. Okay, and it was x of 1, which was 2. Plus, I would integrate from 2 to infinity. Okay, but even on Desmos, we're not going to be able to do that. We're going to take the limit as b approaches infinity of the integral from 2 to b. And I actually really like what I'm going to be able to do on Desmos. I'm going to have to pause it and set it up for us, but I did this once earlier. X prime of t. And so, yeah, I can show you me setting that up. Okay, yeah, actually, I've got the thing right here. So I'm going to replace this with a capital B. And we are going to add a slider for b. And I'm going to let b go from 0 to, I'm trying to remember what it was. I think 50 works. And yeah, step of 1. Okay, but I'm not even going to animate it. I'm just going to slide it myself. Okay, so if we integrate from 1 to 1, we have an area of 2. Okay, well, that makes sense. Okay, now the farther I go on, I'm adding more area, and I'm adding more, and okay, more and more decimals are staying the same, and they're, okay, now I see the limit existing. Okay, we don't usually analyze limits numerically, at least in my calculus class, but that was an example of us doing that. So that's going to be 2.374. And so I would say that the equation of this line that we're approaching is going to be x equals 2.374. This vertical line. But I would also say that this is very possibly exceeds the scope of Cal BC. Okay, but it was a good, exciting problem. All right, now the last example I've got for you is an interesting one from 2003. This is definitely the most unique of all the parametric equation free responses I have seen. Most of them are super standard. But this one, the particle starts at point A on the positive x-axis, and that's t equals 0, and goes from A to B to point C and then point D, and it arrives at point D at t equals 9. That's like the end of our situation here. They're going to tell us that x prime of t is negative 9 cosine of pi over 6t times sine of pi over 2 square root of t plus 1. And they're going to tell us that they're not going to give us y prime of t. We won't need it. We don't need to worry about it. So I've got that loaded into Desmos right here, like x prime of t, calling it f of x. And we actually won't need that until the very last part. So at point C is dy dt positive. At point C is dx dt positive. Give a reason for each answer. Okay, well, that's going to be tough for me because my reason is almost always the sign of a derivative, but that's what they're asking me here. So I feel like I have the tables turned on me. So at point C, the object is moving to the left and down. So x is decreasing and so is y. So I'm going to say dy dt is not positive because y is decreasing. And for dx dt, I'm going to say the exact same thing. As I'm moving through point C, I'm going to the left, so x is decreasing, which means that dx dt is going to be negative, not positive. You can see that. Okay, the slope of the curve is undefined at point B. Okay, when we know undefined is dy dx doesn't exist because of division by 0, so it's going to be like, dx dt or x prime equaling 0. And if you need, you could turn on the graph, and see where does that hit 0, right there at x equals 3. Okay, but you could also just kind of look over at the equation for x prime and say, okay, well, how do I get 0? And it's going to be cosine of pi over 2 is when that happens, and that's when t equals 3. And so either way, we're going to get t equals 3. Let's see is where it really starts to get interesting. This one's a little challenging. So if they tell us the equation of the tangent line at t equals 8 is y equals 5/9 x minus 2, really the key information there is the slope of the tangent line. That's something we can work with in calculus, right? It's the derivative. It's going to be dy dx. They're going to ask us for the velocity vector and the speed of the particle at this point. Okay, so I'm just going to start taking out that 5/9 and just working with that. So dy dx at the point where t equals 8 is 5/9. Okay, and I know how to get dy dx. That's y prime over x prime with t equals 8 plugged in. And I could multiply both sides of that equation by x prime of 8, which is something I'm able to find with a calculator. And I would get y prime of 8 equals 5/9 of x prime of 8. And I'm like, yes, I can go and I can do this with a calculator. I can find x prime of 8. Go here and say, okay, that's going to be f of 8 because f is x prime. And I would get negative 4.5. So I'm going to report that. That's going to be one of the components of my velocity vector. And then the y component is going to be 5/9 of that. And if you are just able to take 5/9 of that mentally, good for you. If not, you're going to go over here and say times 5 divided by 9 and get negative 2.5. That's not that hard. And we can report our velocity vector is going to be negative 4.5 and negative 2.5. And then for the speed, we're going to use those components of velocity because that's how we compute speed, is the length of the velocity vector. So speed is going to be the square root of something squared plus something else squared, and those things are the negative 4.5 and the negative 2.5. Okay, so if I want, I can use the calculator for this because, and for a penny and for a pound, 4.5 squared, positive or negative, doesn't really matter. 2.5 squared, that's going to give me 5.148. And that's going to be the speed. But if you wanted to do that by hand and say that's the square root of 106 all divided by 2, that would be just as good. It's all the same number. So that's our speed. And okay, when considering how far apart points A and D are, okay, I'm going to just draw the diagram. So I've got the diagram there, A and D. If I'm thinking about it, oh yes, they're both on the x-axis, so that's going to be essential for us. That's going to be the thing that they're talking about. I'm going to find that distance there. And the key realization is that the distance here is the net change in x over the travel of the object from time 0 to time 9. And if I want to find the change in x and I have the derivative of x, I need to integrate that derivative, because if I integrate x prime, I will get the net change in x. Okay, so I'm going to go over here, integral from 0 to 9 of x prime of t dt, integral from 0 to 9 of f of t dt. I'll get negative 39.255. Okay. Now that means that x of 9 minus x of 0 is negative 39.255, which that would make sense because we know that the object moved to the left. It just moved to the left by 39.255 units. And so I will conclude, okay, the distance they asked about is 39.255. All right. I think that was a really good collection of Cal BC parametric free responses and all about 2D motion. I feel good about those examples. That's going to be enough for you to try your hand on the homework. So that's going to be all for this video. Thanks for watching.